dar bienvenida hoy día a Rayssa Caju. Rayssa viene de Brasil, pero ya se instaló muy bien en Chile, en Santiago, le gusta mucho, ¿cierto?
Sin comentarios.
Y bueno, Rayssa obtuvo su doctorado en Brasil, en Paraíba, en Universidad Estatal, si no me equivoco, de Paraíba. También trabajó en Princeton con su co-advisor. Después tuvo una estadía en Chicago y después vino a Chile y ahora es profesora de nuestro departamento. Entonces, en cierto modo, este coloquio es una bienvenida oficial para ella, pero yo supongo que ustedes ya la conocen muy bien. Está dando clases y está trabajando full. Y hoy día nos va a hablar del puente entre las superficies mínimas y ecuaciones en derivadas parciales, pero como tenemos algunos participantes que solo hablan inglés, entonces la charla va a ser en inglés. Ok, Rayssa.
Okay, so thank you very much. For me, it's a pleasure to be here today. He was being very polite. My Spanish is actually very bad as well. So my students, they suffer a little bit, but I mean, they are getting used to the portuñol. Okay, so, but I mean, for today's talk, I will try to do it in English, okay? So my goal for me, actually, it's a pleasure to be introduced by someone that is a specialist in the area. I have to say that, sorry. And I will try at least to explain a little bit about this bridge that it's more or less between geometry and partial differential equations, okay? So let me start. So I sort of divided the talk in the following way. I will try to keep it in the very basics, especially for the part in geometry, because I know a lot of you don't know some of the concepts, and I will try to keep it basic at the beginning at least. So I will start talking a little bit about minimal surfaces. I will then move to this bridge that I will try to explain a little bit, which is the Allen-Cahn equation. And then in the end, I will talk about some of my contributions, our contributions in a group, and some possibilities of this topic. So I hope that by the end of the talk, I can sell a little bit of some geometry for some of you guys, okay? So we'll start actually with this very known, let me be here because I'm taller, like that. So I will start with this very known problem, which is called the plateau problem, okay? So actually around 1760, a mathematician called Lagrange, he proposed a following problem, okay? So he did, let's pick some sort of boundary, okay? And let's consider the surfaces precisely with this boundary. So this is the first step. So here we see some possibilities, some possible surfaces with this boundary. So the first one is this. These pictures are a very nice book in geometric measure theory, if any of you is curious about. So this first one is a surface with area pi plus 1. Okay, so we can increase the area, of course, and we can try to decrease the area. So I have a second surface here with area pi plus 1/4. I can do a very, very thin slice, and I can go up, and I can consider a surface with area pi plus 1/16, for instance. And I can continue this whole process, okay? So I can get more and more kinds of surfaces. But the goal of them, especially, they were trying to find the surface with the least area. Okay, so Lagrange, he started trying to understand a little bit of this problem, but this problem was known actually by another mathematician who was trying to study it, with name Joseph Plateau. So in about the 1800s or something, Plateau was trying to play in some ways with this problem with soap films. So here, for instance, in this picture, we have the boundary is this two blue rings. And he was trying to play with soap films in order to determine which of the surface it would form, okay? So this is sort of known by Plateau's problem. And the question is, what is the surface with such boundary with the least area? Okay, so this is sort of the motivation at the beginning. So, oops, I'm fighting a little bit with this, but okay. So, and why soap films? Because from the physics point of view, the soap films, they tend to adopt the shape which sort of minimizes the elastic energy and therefore the area. Okay, so this is sort of the basics, the very basics of minimal surfaces. The idea would be to try to find surfaces with area minimizing properties. Okay, so this is the beginning of the whole story, more or less. So this problem was proposed, as I mentioned, in 1873, but only around the 1930s, it would start to be solved under some constraints by two mathematicians. So the first one was Jess Douglas, and the second one, I will not be able to pronounce correctly, but I will try, was Thibaut Radon. Okay, so both of these mathematicians, they came up with different ways to solve this problem independently. And the techniques had some sort, especially from Douglas, it was all about minimization techniques. So the idea roughly would be, okay, so we have some, no, but okay. So we have some sort of boundary. Perfect. So a very naive idea would be, okay, we have some sort of boundary. We can try to pick sequences of surfaces converging to a certain infimum, and hopefully this would lead to a solution of the problem. So this would be a very naive way to try to solve something like that. So back in 1930s, they managed to solve this problem with some topological restrictions that I will not talk in details. But I mean, this was an achievement, especially in calculus of variations, and originated a whole new area in mathematics, which today is called geometric measure theory. Okay, so geometric measure theory is all about trying to solve geometric problems with some tools from measure theory. And this, because of the solution of this problem, this guy, this other didn't, but this one, he won the Fields Medal. The other one, I don't know why. I have to read with details this story, why only he won the Fields Medal. So it was one of the first, I don't know if it was the first or one of the first Fields Medals sort of for this kind of problems, okay? So this is something about the story, the motivation. What are these minimal surfaces? Idealistically, they are surfaces that minimizes the area. So this is my first message of this talk today. So let me stop fighting with this. So I will try to go a little bit formally, and I will try to explain a little bit more formally what minimal surfaces, what we understand by minimal surfaces today, okay, in modern times. So I don't know who here is familiar with concepts from geometry, but let's assume that you don't know anything about it, and you try to pick a surface. So there is a way to try to determine if the surface is different or not from the Euclidean space. And this way is to try to understand how the surface curves, right? So if the surface curves, this is different from a flat plane. This is the first sort of idea. So there are some concepts of curvature that I will try to explain in one of them. So for instance, I will try to measure the curvature at this point. Okay, so I have a point in a surface. From calculus, we know that we have a tangent plane. If we have a tangent plane, we can try to look at the normal directions here, the normal planes intersecting at the point, right? We pick the surface, we do an intersection, we have a curve inside the surface. And now we look to the curvature of each of these curves. So I will have several different directions and several different curvatures. So I pick the minimum one and the maximum one. These are called principal curvatures, okay? So one of the ways to define one of the special quantities, which is the mean curvature, is to pick these principal curvatures and sum. So this is called the mean curvature. So why am I at this point trying to introduce this new quantity? Why am I trying to introduce a curvature quantity that's at this point unrelated to minimal surfaces? Okay, because I'm trying to define minimal surfaces as something which is a minimum of the area. So if this is a minimum of the area, this should be a critical point. So if I try to understand, for instance, critical points of the area function, I try to, I don't know, pick a surface, we consider variations of the surface, and we try to take the derivative. We look at the formula. So the derivative of the area is this beautiful thing here that depends on this variation. So I can attempt to draw this, but I think the picture here is a little bit more clear than my drawing. So what we are doing, we're picking the surface and we are deforming a little bit, and we are taking the derivative at this deformation, okay? So we look to the first variation of the area. So we define formally, a little bit more formally now, minimal surfaces as critical points of this area function, okay? This is one way. But if we look to this, if this here is 0, if and only if the mean curvature is 0. So you will see in several places that people will define the concept of minimal surfaces as a surface with mean curvature 0. This is a very polite way to try to explain this a little bit shortly. If I want to traumatize you a little bit, I can replace my ambient here, R3, by a manifold, okay? I can try to do this, and I can define minimal surfaces inside, for instance, a sphere. I can define minimal surfaces in a toroid. So I can define in several different ambients in the same way, trying to define minimal surfaces as critical points of the area function or surfaces with mean curvature 0. So this is the first step of the way. So I try to pick some practical examples, and I know that there's a lot of applications of minimal surfaces showing in nature, for instance, but I try to pick 2 for this talk to keep it simple. So one, it's one of my favorites. In architecture, they try to use this type of surfaces a lot. So this one here is a very famous construction of the Olympic Stadium in Munich. Sorry for the pronunciation, but I mean, the architect was in Germany at that time. I read that he was sort of tired of all the buildings being built in blocks of concrete. And he was known by trying to approach things in a more elegant, in a more nature-like way, and also in a more low-cost way. So he took inspiration on minimal surfaces to try to build the roof of this stadium here. So this is one of the many applications that we have that are very practical today. And the second one, this is sort of a project from the Institute for Advanced Architecture as well in California, where they were trying to build something that would integrate nicely. So this also have a name. I think it's called biomimicry, that it's something that you try to mimic nature, and they like it a lot. Things like that. I find it beautiful, but I mean, that's all about it. So this, it was a project trying to glue, I will try to show to you Costa surfaces, okay? So these are two sort of practical examples. I put it here, some sort of citation that it's more or less inspired by the pictures by this idea of trying to build things based on nature in some ways, okay? So yeah, I'm fighting with this. I don't know why, I'm sorry. So another classical example of minimal surfaces here for the physicists that I will claim that I don't know much about this, but I know that it's very related. So in black holes, in the study of black holes, when you have a black hole, you have something that it's called event horizon. Sorry, honey, if I mess this up. So the event horizon is sort of some sort of the boundary in which light and anything cannot escape anymore from the gravitational force of the black hole. This is what my mathematical training tells me. And what they tell you is that the horizon of this black hole is a type of submanifold. And if you try to see slices in time, you would have that this here is, in special cases, a minimal surface of this slice. Okay, so minimal surfaces are very important, and I know that people really apply this in trying to understand the phenomena, but this is sort of an example, very simple for this talk. Okay, so here let's start by seeing some basic examples. So mathematicians are trying to find minimal surfaces for a while now, and it started with Lagrange, but the first more or less interesting examples were given by Euler, the example of the catenoid. So this surface here, the first one is called a catenoid, and the second one, this was the first one discovered besides the plane. The plane is the simple one. So the second one here was discovered by Meusnier in 1776, I think, with some collaborations from Euler, if I'm not mistaken. And this second one is a sort of periodic surface, which is called the helicoid. So these two are the first examples, let's say that way. So it's been quite some time since people didn't find any sort of example, and then they came up with this one. This is the Schwarz surface in a way. So what people did right here was, okay, we know how to solve the plateau problem. We pick the boundary as a triangle, two triangles. We solve the plateau problem and we repeat. Something like this, okay? So this was sort of the third, more or less, example that came up. So here, this is a very nice surface, but it has a problem in some ways. There are too many holes, and these holes are related to the topology of the surface. So in a way, the surface here has infinite topology. So, and now is the point that I arrive at the Brazilians, that I have to sell my country for you as well. So there was a mathematician working in the 80s called Costa, Celso Costa actually, who found the first, after the catenoid and helicoid, the first minimal surface with, I think, genus 3 holes, okay? Which means limited topology that are different from the catenoid. So it was this quest for minimal surface. People were trying to find them, and then Costa found this first example here. Okay, so this was a revolution to the area and revived the area of minimal surfaces, especially in Brazil. That's why we have such a large school there. And after that, of course, people started to build even more examples. And there is this very nice one by Costa Hoffmann-Mix. So they tried to construct surface with many, many, many holes. Okay, so these are nice looking pictures. Of course, they are not mine, but here are the if you want to see the website of this guy here has a lot of beautiful examples of minimal surfaces for you to play. Okay. So I'm showing you at this point only things inside the Euclidean space, but I can also get examples of minimal surfaces, for instance, inside the sphere, because I can define the same way. So in the sphere, let's consider the basic sphere S3 in R4. Okay, so the equators are the basic examples. This is the first basic example. The second basic example, it's called the Clifford tori of torus. I never know how to pronounce this. So this is sort of almost the second example of a very simple minimal surface. So since these things are in R4, you have to take a stereographic projection in order to try to see the Clifford tori this way. Okay? So you're getting spoilers all the time because I don't know how to use it. So, and after the Clifford tori, that is something with some sort of topology because it has a hole, this guy, Blaine Lawson, he proved that for every single number of holes, in a way, every single number of genus, you can produce a minimal surface inside the sphere with such given genus. Okay? So these are as well pictures taken sort of think in considering the stereographic projection, because I mean you cannot see the R4 here. Okay, but I mean these are examples. You see that you start to increase the number of holes, the number of topology that you have in your space. Okay, so these are basic examples only to motivate a little bit. And a lot of mathematicians actually they contributed to the development of minimal surfaces, especially in this case of the sphere. But I want to highlight that the theory was revived in a way by two mathematicians that this one happens to be one of my co-advisor, but they started at some visit. I don't recall the university. They were at the university doing a visit. So they started to dig in a very obscure works in minimax theory by this guy called Allen and also Pitts. So they sort of started to study these works, and based on the techniques of minimal surfaces and geometric measure theory, they proved the long-standing conjecture in the 60s. I will not enter in details about this conjecture, but I mean, if you're curious, it's called the Wilmore conjecture. So they proved this Wilmore conjecture, and based on this, they finished more or less building the whole Almgren peak, sort of a minimax. So a minimax is a way to obtain critical points that are minimal surfaces here. And proving the Wilmore conjecture, they moved to prove another conjecture with one PhD student, actually, which is called one-to-one song. So they managed to prove something that it's called the Yau conjecture. So they managed to prove, for instance, that inside a sphere, you can find many, 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 or infinitely many minimal surfaces. So this was a very nice thing, because by this point, we know that examples were hard to find. So to obtain a result that proved that minimal surfaces existed, but also existed in abundance, in a lot of variety, this was an achievement for the area overall, okay? So the theory was sort of developed, and today the minimax is a very nice and very powerful theory, okay? So this is a citation by Shane, a mathematician a famous geometer. Okay, so this sort of concludes my first trying to motivate the part of minimal surfaces. Let me see, and now I will move to try to justify this bridge, which is the Allen-Cahn equation. Okay, so I motivated this part, and I will try to connect now with PDEs. So I think around the 60s, more or less, Allen and Cahn, they were studying some phase transition phenomena based on this very simple, very nice looking equation here, where here I can sort of write down W is something like this. So they were trying to study, here my chemistry may fail, they were trying to study these anti-phase boundaries in alloys between two different materials. And they were verifying a phase transition separation that was modeled by some PDE. And as we know, PDEs, solutions of PDEs are critical points of some sort of functional. Okay, so I'll write the energy function associated with this PDE. So this is a picture of the paper by Allen-Cahn. This is the original paper where all these things sort of came from. So yeah, this is not working pretty often. Okay, so by that time, more or less in the 70s, there was a school of mathematicians. I put some names here. They realized something. They realized that if we take a look at the solutions of this equation, this is a PDE now. We take a look at the solutions of this equation, the energy of the solutions were sort of converging to the area of the thing that was appear between the transition of the phases. So I have here is sort of representing the surface and representing both of the materials somehow. So here we have one of the parts, the other one, and we have this transition region. Okay, so they connected solutions, or which means critical points of the energy, to this equation here. They connected with the area of this transition region as epsilon goes to 0. Okay, and what they realized is that this here that was appearing in the middle was sort of a minimal surface, and here is the connection. Okay, so this is the thing. So this equation sort of in the limit, if we take a look here, there is this transition region and it's precisely a minimal surface. Okay, so this is more or less a formal explanation. Okay, so I showed to you now that there is a very nice looking equation that can help us, that connects in some ways with minimal surfaces. Okay, so I have a first question. Can we obtain information of minimal surfaces using the equation, using the Allen-Cahn equation? So this is my first question. So I will put here my colleagues in, because they contributed a lot. So two mathematicians, one that works here in Chile and another one that right now works in Imperial College. They're both students of Fernando. They managed to find sort of an alternative minimax. So I mentioned before that there was this sort of Almgren-Pitts minimax. And now they managed to find an alternative Allen-Cahn. Let me write like this. minimax they defined in these papers. I'm putting them, but I mean, this was a work by a lot of people, but I mean, they managed to formalize this in the paper, and they managed to find this alternative minimax to the Allen-Cahn equation. And why do we need that? Why is this good in any ways? Because this minimax here that worked to find minimal surface, this was very, very complicated. So they did a minimax based on a PDE that it's much nicer looking. So they managed to try, through Allen-Cahn, they managed to prove a version of the Yau conjecture, which means they managed to find infinitely minimal surfaces inside an object, okay? So through a PDE, they managed to prove a result in minimal surfaces. So this is sort of the part that I want to highlight here to really enhance and highlight the connection and how precious it is to have both of these tools. Okay, so the second question from a PDE perspective is that now, can we obtain information of the Allen-Cahn of the equation based on what we know about minimal surface? So this is the opposite question, more or less. So for instance, can we obtain any sort of classification? Can we understand the solutions based on Morse index on if the solution is stable? So here, a reminder for you of the definitions. I don't know if you see in the PDE course here, but here is sort of the definition of Morse index and of stable solutions that are solutions with 0 Morse index, okay? So this is sort of known, this is related, I put it here, to the Di Giorgi conjecture. So the Di Giorgi conjecture is that if you have a solution of the Allen-Cahn, the Giorgi conjecture that if the solution is monotone, the derivative in one of the directions is increasing, and the solution is limited, then the solution has to have a phase. So this is sort of a classification conjecture in some ways. And this conjecture was actually motivated by also a conjecture on minimal surfaces. So I'm enhancing by both sides this connection between the equation and minimal surfaces. So here I put it some of the main contributors for this, the resolution of this conjecture, and of course we have one here. Okay, so this is sort of my take on this part on the Allen-Cahn. Okay, so I explained to you a little bit the first part, which is minimal surfaces, really trying to motivate. I presented to you an alternative using solutions of search-determinant PDEs, and now I will try to move a little bit for what we did, what we tried to contribute. So the first thing that we tried to do was always based on this analogy, was to try to study existence of solutions. So, for instance, we consider the problem. If we are inside a manifold, let's see, so now if I have a manifold here and I have a surface in my manifold, okay, so if I give the minimal surface, can you construct solutions of the Allen-Cahn equation sort of converging to this minimal surface? So this was the first question that we tried to understand. So when we tried to understand this question, we saw that there was some works by Mike and also by Paca and Hitore that solved the cases where your surface had some sort of a specific property. So especially the work of Paca and Hitore, they assume that the kernel of some linearized operator is trivial. So the surface has a property that it's called non-degeneracy. So this is the only part that I want you to, the non-degenerate, to focus, okay? So the problem for us, what we were very interested in the case of the sphere, for example. And the case of the sphere was such that if you consider the sphere has some symmetries. So for instance, you can rotate the sphere and this should be fine. So because of the symmetries of the sphere, we knew that in such cases, in determined cases, there was no hope of this hypothesis being met by every single minimal surface, especially the ones that we were interested. So here is a way specifically to try to produce these elements of this kernel of this operator using these isometries, these symmetries that your surface has. Okay, so oh god, I think I will try to use the computer next time. Okay, so in our case, we knew that we had some sort of elements in the kernel. So we tried to solve the problem by, okay, if we have elements, but if we know who the elements are, we can try to solve it. So this was basically what we tried to do. So with sort of this hypothesis on hand, and this paper is to appear forever, we managed to build solutions of the Allen-Cahn equation for several cases, including the sphere, such cases with symmetry, for converging to a given minimal surface. So this is sort of a summarization. So I'm trying to summarize here what we try to do. And in the very particular case of the sphere, that is the case that I'm mostly interested in, it is expected that these elements of this kernel always comes from these symmetries. So for the case of the sphere, is expected, the expected conclusion is that every single minimal surface in the sphere can be obtained as a limit of the Allen-Cahn equation. So this is sort of the main message at this point. Okay, so this was the question 1 that we did. How much time? You know? Okay. 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 I tend to be too fast. Okay. So the second part that we tried to understand was sort of characterization. Okay, we try to understand solutions. So now it is. So we return to one of the questions that I previously put in the slide. So again, I will repeat the question. Can we get information about solutions of the Allen-Cahn based on the analogy with minimal surfaces? So this was the question that we sort of did in this case. So we tried to look at the case of minimal surfaces. So for minimal surfaces inside the sphere, that was known that there were no stable ones. Okay, and in parallel, the only solutions that were stable to the Allen-Cahn equation were the trivials, constant solutions, plus, minus 1. So this was okay. So we passed from stable minimal surfaces. Let's perturb the surface a little bit. Let's allow that the surface has some sort of perturbation. So we try to look at index 1 solutions. Okay, so if you're curious, this is related to more theory and a lot of things. I will try not to define a lot here, but we try to see the next non-trivial surfaces. This is my question. So for minimal surfaces, there was this very famous result by Simons that sort of showed that index 1 hypersurfaces had to be equators inside the sphere. So we try to look to this result. So the question that we did for Allen-Cahn, so we know about minimal surfaces, we want to know about Allen-Cahn now. The question that we did was, can we characterize, can we understand index 1 solutions of the Allen-Cahn equation? So this was our question at this point. And this can be more or less seen as sort of a version of this classification result of the de Giorgi conjecture in the sphere, sort of, okay? So this was the question that we did. Can we understand, we know who is the most basic solution. Let's try to take a look in the next one, in the index 1. And when we got to this question, we saw, okay, so trying to look at index 1, Morse index 1 solutions may be a little bit too complicated for us right now. So what we did was, let's try to take an easier class first. So again, I know there are a lot of people who works in PDE here. So in PDE, you can try to look to the least energy solution. You have your PDE, you have a functional associated to the PDE, you can look to the energy. So you look to the energy of the first non-trivial solution that you have. This is called my ground state solution, okay? So this is very trying to simplify everything, but we look to this class. And okay, what can we say about the ground state solutions? So we showed basically two things here. We showed that the ground state solutions were indeed radially symmetric, decreasing. And for the ground states, I had some sort of characterization. That this was the thing that I started talking about. So we showed some sort of characterization. And we showed a little bit more. Not only that the solutions were radially symmetric, but we found the nodal set. So, okay. So in a picture, this result that we got, if we are in this sphere, we show that the solutions are radially symmetric. Okay. Here. So the solutions are all radial. And they are zero precisely on the equator. That it's truly the analogy that we want to base it on. I will try to return the slides, but let's see if here. It was precisely the analogy with the result by minimal surfaces, since index 1 hypersurfaces were equators. But we only got this for ground state solutions. Okay. So we also got something interesting, that it's a cute result in bifurcation, sort of. We studied in, at least in S3, this was very specific for dimension 3. We don't know why, but we tried to take a look at the solutions, and we also saw something like this. So for some epsilon, here I only have constant solutions. So when we move the epsilon a little bit, appeared precisely the constant solutions and these ground states that accumulate around the equator. So we moved a little bit. Again, we started seeing more solutions. Solutions accumulating in other kinds of minimal surfaces inside the sphere. So this was a very nice result. We were sad that we weren't able to get this for higher dimension, but this is sort of a nice way to put it. Let's say that. So we got all of a partial answer. So the question was, can we characterize index 1 solutions in the sphere? So we characterized ground states. Indeed, we showed that the ground states were radial and had that behavior of the picture. But we knew from previous results that ground state solutions had index 1. So we characterized only a part. But it was a nice answer, but the problem is still open. Okay, so this was sort of the part that I wanted to sell. And I want to conclude this talk by trying to say the following. I try to justify here that with the knowledge that you have from PDEs, there's a very nice possibility of studying this very nice geometric objects that are called minimal surfaces. And also that the minimal surfaces can give you some answers about the equation. So you can deeply try to explore these connections. Okay, I hope I managed to justify a little bit. And to end, The dream would be to conclude this study of this sphere, of course, to indeed characterize all the index one solutions. But we also wanted to understand this problem if we pass from the sphere to a ball. And why is that? Because when we get a ball, we get a boundary. So there is this very nice idea of pre-boundary minimal surfaces that people study a lot. So this is the nasty one. So this surface here has given a lot of trouble to mathematicians. And there is a very famous conjecture that I will only say here in the end, that it's called the critical catenoid conjecture, that it's giving a lot of trouble about this object. Okay, so the goal that we had would be to pass the problem from the sphere to a ball, to try to understand similarly, in a very similar analysis, this sort of objects in this context, disks, critical catenoids, and a lot of other surfaces, free boundary surfaces in this case. So now this is the end of my talk. Thank you all.
Avelio.
So I had a question. You said that there were infinitely many minimal surfaces on the sphere. I was wondering whether there was a natural measure on them which respects some kind of symmetry they have between them.
Symmetries.
Or like if there is a measure, like a natural measure, whatever that means, on top of minimal surfaces.
Okay, so I know that they obtained, together with this result, some sort of equidistribution result about the minimal surfaces that they found. Some sort of bio law connected to this. So, but I mean,
a probability measure, like is it has finite measure or is it infinite?
I don't know with details, but I mean, the only thing that I know in this part is that they found this bio law to try to have some sort of measurability or something like this. But I mean, they have the bio law, they have this equidistribution result, but I really don't know if they have this way to think. I mean, yeah, this is
the other question I have. So I don't know if I get exactly the Allen-Cahn equation, but what, like, you have this potential W?
Yes.
So what happens if you put a so it's always like a double well, or
yes.
is it whatever? It has to be like that. It
yes.
cannot be whatever.
I mean, for the cases that I was trying to approach in the talk,
okay.
It has to be something like this. So 2 minimums, 1 maximum.
Okay. Yes, I was wondering what happened if you randomize this W, but I think it is a little bit too nice. Okay. Thank you.
Sorry. There. Yes, the do you mean the plateau problem? Minimal surfaces. Oh, okay. So the plateau problem was inside the R3. So the plateau problem was basically I had a plan to try to attempt to reproduce the experiment here, but I realized it was the probability of getting too messy was too high, so I gave up on my plan. But it's like this: you pick some sort of boundary, a contour, and you try to play a little bit with the contour. You fix the contour, but inside the sphere, your surface that you are considering, there is no boundary for this. So inside the sphere, the things change a little bit. So if you go, for instance, if you go here to the ball, indeed there is a boundary here touching, right? So in the ball, there is this boundary touching. But if you're in the sphere, so this thing that contains is sort of a surface with dimension 1 less than the whole sphere, but there is no boundary. So this is this is sort of the way that I would try to put this. Is it too bad? Sorry.
More questions?
Well, thanks for the nice talk. Yeah, thank you for the nice talk. So you said that ground state solutions are inside this space of index one solutions.
Yes.
Is there any finer classification for the complement? So index one solutions which are not ground state.
So we actually believe that. So we believe that all index one solutions are ground state. We don't know how to prove, but we believe that. So this is the problem. I mean, the ground states are inside. We know that ground states are precisely index one. If we knew how to prove that index one are ground states, the result would be good. So we believed at some point that it was probably the way to prove the result, to prove that index one were ground states. Let's see.
Okay, more questions? All right. If there are no more questions, so if there are no more questions, let's thank Rayssa again. Attending the colloquium.
So, like I don't know random announcement, but not so important announcement. So there is a poster downstairs on the sheet. Okay, and
Okay.
so welcome there. The last session of the colloquium of will week break.
Presiona essa, você sai dali. Okay.
Almost fully.
Very nice.